Today we're going to look at quadratic functions and models. We've already looked at a few basic functions, and you can see those three listed here: the linear function, the constant function, and the squaring function. And all three of these are examples of polynomials. Poly means many, nomial just numbers or terms. So anytime you have one or more terms, you have created a polynomial. The strict mathematical definition of a polynomial can be seen here in the green box. You have n being a non-negative integer. Why do we say non-negative? Why don't we just say positive? Because 0 could be included in that. Non-negative means that it can't be 0 and that it has to be positive all times. So then we have these a sub n minus 1, a sub 2, so on. Those are real numbers. Those are our coefficients on the polynomial. And the strict mathematical definition of the polynomial is given in the middle here, where you have f of x equals a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power, and so on, until you get down to the a sub 0, which will be your constant term. This is called a polynomial function of x with a degree of n. So whatever the highest power is identifies the degree of that polynomial. Constant function has a degree of 0. If you imagine, for example, y equals 3, what that simply means is that's the same as saying y equals 3 x to the 0 power. X to the 0 power is just 1. 3 times 1 is 3, so we end up with a constant function. So a constant function has a degree of 0. Linear function has a degree of 1, so we could consider 2x plus 5. That's linear. The degree on x is 1, so this is a degree 1 polynomial. Some other special functions that we're going to be looking at, well, not necessarily special, but our main focus of this set of notes are quadratics, and quadratics are degree 2 polynomials. And you have 5 examples listed here in the middle of your screen: x squared plus 6x plus 2, and so on. The last example, the m of x equals the quantity x minus 2 times the quantity x plus 1, initially does not appear to be quadratic in nature, but when you go ahead and distribute the x minus 2 through the parentheses for the x plus 1, you do in fact end up with a quadratic function with an x squared term. The strict definition for a quadratic, again, we're talking about a, b, and c being real numbers. So they can all be positive, negative, fractional, it doesn't matter. The only stipulation is that a cannot be 0. If a is 0, then our quadratic function is reduced to a linear function. And you can see that right here, where we have f of x equals ax squared plus bx plus c. If a is 0, then this term disappears and we have a linear function. We just left with bx plus c. It's no longer quadratic. The graph of a quadratic is a parabola. We've talked about this. Actually, we talked about it together in person yesterday. Several of you were able to accurately depict that. Some of you drew your fingers in the air and showed a U shape. But all quadratics, they do have that U-shaped graph. And we have a couple of properties about that particular U-shaped graph, which is called a parabola. If the leading coefficient, if a is positive, then our graph opens up, and you can see that right here in this diagram. It shows ax plus bx plus c if a is greater than 0. So that just simply means that our leading coefficient is positive. For a leading coefficient a that is negative, or a is less than 0, our parabola opens down. And there's a couple of things that we want to point out on both of these graphs. One, if the graph opens up, then this vertex is a minimum value. If this graph opens down, then our vertex is the maximum value. That's the highest point that graph will ever reach. Consequently, on the other graph, if it's a minimum, that's the lowest point that graph will ever reach. And when sketching these graphs, it's often helpful to compare them to the graph of y equals x squared. And this is going to go into some transformations that we have looked at previously before. But let's first go ahead and consider for part A, we're looking at y equals x squared. And we know that graph is going to look like the parabola with the vertex at the origin. That actually didn't turn out half bad. I'm kind of proud of myself. But there's our graph of y equals x squared. And we want to compare that with 1/3 x squared. So what that would simply be, our origin is still the same, but now if we put in 1 into that function, we get 1/3. If we put 2 into that function, we would get 4/3, which is the same as 1 and 1/3. If we put in 3, which is 9, that's 9/3, which is actually going to be 3. So we can plot this graph. Man, I'm on my game today. My graphs don't look that bad. They're not great, but they're not horrible. And that's what we get for part A. That's 1/3 x squared. Let me just illustrate that here. Okay. So what we notice there is that this graph, that they have a similar shape. We're comparing that to the blue graph of x squared, but it's been compressed vertically. So it's been something, it's almost like you set a weight on the graph and pushed it down. And we're going to talk about that here in just a second after I do this part B. So again, part B, we're looking at the graph of x squared. I bragged on myself, and here's where the graphs are going to fall apart. Not too bad. Okay, so there's x squared again. And I'm going to use pink this time for 2x squared. So the origin is still at 0, but now when I put in 1, I get 2. And when I put in 2, I'm going to go up to 8, actually. So that's going to be somewhere up here. And my graph is going to look like this. That could have been better. 2x squared. And what we notice here, the pink graph compared to the blue graph, that graph has been pulled upwards. And the key component that makes these two transformations happen in part A, our A value, the leading coefficient, is between 0 and 1. Okay, so if your leading coefficient is between 0 and 1, you will get a vertical compression. If your leading coefficient is greater than 1, which we see in part B, so it could be anything larger than 1, you're going to get a vertical stretch, and that graph is going to actually get drawn closer to the y-axis, whereas if it's compressed, it's going to get pushed down closer to the x-axis. Standard form of a quadratic function is what we're getting ready to talk about on this next part, and the standard form of a quadratic is given by f of x equals a times the quantity a minus h quantity squared plus k, and hk is the vertex of the parabola. That's where that minimum or maximum value occurs. And if we have a couple other notes here in the green box. We have that the graph of the parabola, it has an axis which is the vertical line x equals h, so whatever the x coordinate of that vertex is, that's our axis of symmetry for this graph. The vertex is the point hk, and again we talk about if a is greater than 0, the parabola opens up. If a is less than 0, the parabola opens down. And we're going to put that into practice here with example 2. And I skipped over the note there. To graph the parabola, it's helpful to begin by writing the equation in standard form using the process of completing the square. And we're going to do that here in example 2. We're going to complete the square to graph this. So our original function is 2x squared plus 8x plus 7. One thing that I will note before we get started, let me write this out. These first two terms, they have a factor of 2 in common. I know they both have an x in common, but we want to leave the x's alone. We want to keep this in x squared. So let's factor out a 2. And so now we have x squared plus 4x plus 7. And I put that in parentheses now because I factored a 2 out of those two terms. Now, when I am completing the square, remember to complete the square, we take half the linear term. So in this case, it's 4 over 2, and we square it. 4 over 2 is 2. 2 squared is 4. So this is what we're going to add and subtract from our value of inside the parentheses. And you'll see why in just a second, why we're adding and subtracting. So this is going to give us 2x squared plus 4x plus 4 minus 4 plus 7. Plus 4 minus 4 is just 0. So I've not changed the value of the function itself, but this does help in regrouping terms so that we can factor a perfect square trinomial. I'm going to leave the positive portion, these first three terms, I'm going to leave those alone, and I'm going to take that negative 4 and I'm going to go ahead and multiply it by the 2 that's on the outside. So this 2 will distribute to this negative 4 for right now. Two times negative 4 is negative 8. Okay. We still have to distribute. We've just taken one term out of that whole set of parentheses in the previous step and went ahead and multiplied it by 2. If we were going to do this, distribute the 2 through the whole thing, every term would get multiplied by 2. We still have maintained that property right here by leaving the parentheses, indicating that 2 still has to be distributed to the remaining terms. We have simply just multiplied it by the final term that was in that set of parentheses. Now we can combine our like terms, and we get 2x squared plus 4x plus 4 minus 1. And what's nice about what's inside the parentheses now, it is a perfect square trinomial. That perfect square trinomial simply factors into, we go back up here to this 4 over 2, which we know to be 2. That number 2 is what we're going to use for our factoring of the perfect square trinomial. So we end up with 2x plus 2 quantity squared minus 1. So whatever your term is that you square in this step right here for completing the square, that's what's going to end up in your factored form at the very end of the problem when you completed this step. So this does appear to be in the form we were looking for, which is y equals a times x minus h quantity squared plus k. So this tells me what my vertex is. My vertex is hk. And in this problem, h is going to be negative 2. Notice the signs. That's what you have to pay attention to. So the only way that that could be a positive 2 in my solution right here is that for h to be negative 2. And k is going to be negative 1. So my vertex is at negative 2, 1. So I'm going to go ahead and plot that on my graph, negative 2, negative 1 rather. So there's my vertex. I know that it opens up because A is positive, and it's going to be compressed. So the graph is going to look nothing like what I just drew. Something like this. And the key here is a sketch. We're not doing an exact graph. But obviously we don't want to draw something that is definitely flattened out like this, because A in our particular case is greater than 1. So this graph will be vertically stretched somewhat. But that's how you complete the square to plot the function using its vertex. Finding the x-intercepts. Again, this one is going to be pretty straightforward. We want to complete the square on this one as well. Actually, let me look at it for just a second. Yeah, let's go ahead and complete the square so that we can identify the vertex more easily. We're starting off with f of x equals negative x squared plus 6x minus 8. I'm going to combine these two terms within parentheses, and that's where I'm going to complete the square. So again, I'm going to take half of my linear term, which is 6. I take half of that, I get 3. and then when I square that, I get 9. So just like in the previous example, I am going to add and subtract 9. I don't have anything that I need to distribute, so basically we can think of it as a 1 out in front of the parentheses. So I have negative. Actually, I know what? Let's factor out the negative. Let's make this a positive x squared for the sake of argument here. So let me go back up. I'm going to change things up just a little bit. I apologize. This is going to be negative x squared minus 6x plus 9 minus 9 minus 8. And now I can combine like terms. I have to distribute the negative though, so I have negative x squared minus 6x plus 9 minus negative 9. Distribute the negative to that negative 9, that's where that came from, minus 8, and that will be negative quantity x squared minus 6x plus 9 plus 1. And I also should be more careful here. This should be negative 6, so that'll be a negative 3 squared. When I factor this, I'm going to use that negative 3, and we get negative x minus 3 quantity squared plus 1. So what I know about this graph is it has a x-intercept, or a vertex at 3, 1, so positive 3, positive 1, and it opens down, and I need to find where does this function cross the x-axis, what are its x-intercepts. So I'm going to go back up here, and we're going to factor this polynomial. So I have negative x squared minus 6x plus 8. And the way that will factor will be negative x minus 2, x minus 4 equals 0. The zero product property tells me that I will have a factor of 2 and a factor of 4. So I cross the x-axis at positive 2 and positive 4. Oh, I jumped one. There we go. And we, again, like I said, we know our graph opens down because A is negative. And there's our graph. For example 4, we're going to write the equation of the parabola in standard form using its vertex and the fact that it passes through the point 0, 0. So just one more time, vertex form is y equals a times x minus h quantity squared plus k. Substituting in our vertex values of 1 and 2, right now we have y equals a times x minus 1 quantity squared plus 2. And here we can use the fact that it passes through the point 0, 0 to solve and find out what our a value is. So if I replace y with 0, x with 0, and I simplify this, I get 0 equals, this is going to simplify to negative 1. Negative 1 squared is 1, so it's just a plus 2. Subtract 2 from both sides, and you get a is equal to negative 2. So to write this in vertex form, I replace a with negative 2, and I have y equals negative 2 times x minus 1 quantity squared plus 2. That is standard form of the parabola with the vertex at 1, 2 that passes through the origin at 0, 0. Some applications, we can use these quadratics to find ballistic trajectories. We can look at the path of a ball as it travels through the air or any other projectile. You can look at parabolic reflections, say in a satellite or even in a concave or convex mirrors. It just depends on anything that you may be looking at. So there are actually practical applications to this. And a lot of these are centered around finding the vertex of the graph. And the vertex of the graph is based off standard form. Predominantly, we're looking at the values for B and A. So the x-coordinate of the vertex is negative b over 2a. So whatever our linear coefficient is, divided by twice our quadratic coefficient will be our x-coordinate, and then our y-coordinate is just the function that we're given evaluated at that specific x-coordinate. We'll see that in our next example. So here we've already talked about this in this steps 1 and 2 that you see right here. If A is positive, then the vertex is a minimum. If A is negative, then the vertex is a maximum. All right, example 5. Suppose that a baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees with respect to the ground. The path of the baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where f of x is the height of the baseball in feet and x is the horizontal distance from home plate, also in feet. What's the maximum height reached by that baseball? So all we're interested in, we know that based off the function that we're given, that this parabola opens down, and so its vertex is a maximum. And its vertex, the height is going to be found by finding first how far away from home plate the ball gets, which is our x distance. So if we imagine this just as a sketch real quick, let's say this is the path of the ball. Here's our vertex. So we have this x value is the distance from home plate. This y value is the height of the ball. So we'll begin by finding the x-coordinate, which is negative b over 2a. And from our given equation, b is positive 1. So it's going to be negative 1 over 2 times negative 0.0032. And when I simplify that, that's going to be approximately 156.25 feet. Now that's how far the baseball is from home plate. We need to find how high it is when it reaches that point. So we take our given equation and we evaluate it at 156.25 to find that height, which is our y value. So negative 0.0032, 156.25 quantity squared plus 156.25 plus 3. When we type this in on our calculator and simplify it, we get that the height of the baseball is approximately 81.125 feet above the ground. That is the height of that ball, given the criteria that we have for example 5. Example 6 is a minimizing cost function, and we can do the same thing with a maximizing cost function, but for this one we're minimizing cost. Small local soft drink manufacturer, let's say LA, has daily production cost of C equals 70,000 minus 120x plus 0.075x squared, where C is the total cost in dollars, X is the number of units produced. How many units should be produced each day to yield a minimum cost? We want to make sure that this company is not spending too much money on production. In this particular case, all we're interested in is the value for X. We're not interested in finding what the actual cost is. We're just interested in finding X. Because our A value is positive, we know that this is going to be a minimum wherever the vertex is at. So to find the vertex, again, it's negative b over 2a. B in this case is negative 120. And A is 0.075. When we simplify this, excuse me, it ends up being positive 120 over 2 times 0.075, which is going to be approximately 800 units. So this manufacturer, if they want to keep their cost to a minimum, they want to produce 800 units. If they produce more than that, they're increasing their cost. And actually, if they produce less than that, they're increasing their cost. Because this isn't the exact graph, but this is kind of what it looks like. It's this parabola that opens up. At this vertex, this is where we have the minimum cost. And once they start moving to the left, or to the right rather, increasing production, so more units than 800, then our cost starts to go up. When they start decreasing production, cost also starts to go up again, because it's going to cost them more money to produce fewer units because they have to sell them at a higher cost. Demand's going to go down, and we'll talk about supply and demand some other day. But there are your problems. 1 through 6, just identify the vertex, axis of symmetry, and the x-intercepts. 7 through 12, find the standard form given the vertex and the point. And then 13, 14, and 15 are application problems. If you have questions, ask me. Hope you guys are doing great. And actually, you'll probably be watching this while we're sitting in class together, maybe. I don't know. And for those of you that are going to be staying at home, I do hope to have our first hybrid Google Meet tomorrow. So everybody take care. I'll talk to you soon.